Alright, so let's review we were discussing the surface integral formulation, and so let's just review what we have done so far. So remember, we had these two equations. Yeah, I had this equation and this equation, which I had subtracted, done some algebra and so on. So let's just have a look at what we have done so far. So what we had, this was the left hand side, right, which we had integrated over this. It's a 2D problem, so we had integrated over the whole surface, right. And on the right hand side, we had how many terms? 2 terms, right. The common terms of k1 squared had got cancelled off. So what I was left with on the right hand side is, so let's go back to these terms over here. So I had, right, so this term over here, so g1 that was the first term, and then I had these were the terms that we had, so right. So this is just reviewing the terms that we had, and of course this whole thing was integrated, both sides were integrated over S. Remember S because it's a 2D problem. In 3D it would be a integral dv, that's the only difference. Then we had used one identity of vector calculus to convert this into a del dot something, and what was that something? G1 grad phi 1 minus phi 1 grad G1, and this remained as it is, right. This was over the entire, this was over V1, and then after that we used the divergence theorem in 2D, and that came with a minus sign, right. So this became minus integral, right, over S okay. So that was the left hand side. That minus sign came because we chose n cap as the inward normal, not outward normal, okay. So this was due to convention. Okay. So this was the left hand side, right. What happened to the right hand side? So one small change in what we did last time, we had defined this integral g1 qr as phi I. I am going to change that just a little bit by a minus sign, okay. That is just the convention. So we are going to call this minus phi I, phi incident, okay. So this is going to become minus phi incident of r prime, because the r coordinate has been integrated out, and then I am left with this integral, this over here, right. So phi 1 r prime delta of r minus r prime ds integral, right, over V1. And this term over here, there were 2 cases, is equal to phi 1 r, sorry, this should be a r, right. Right. So this should be a phi 1 r prime if r prime belongs to V1 and 0 if r prime belongs to V2. Okay. So what are the physical interpretations that we can draw from this? Okay, so that's what we'll look at now. So if I rearrange this, okay, I need not rearrange this. So what am I saying? What am I sort of seeing over here? If I just rewrite, if I look at this, these terms that I have, so I have, let me write it on the left hand side now. Okay. So these are the 2 cases, and is equal to what? So let me move everything else onto the other side. So phi incident I will take on the other side, r prime, okay, and this other term remains as it is, right. So I have a g1 grad phi 1 minus phi 1 grad g1 dot n hat dl, right. And remember, this was over this volume over here, V1, that's where I was integrating. Okay. So now let's just try to give a physical interpretation to these equations. So let's take the first case over here, when r prime belongs to V1. So what is it saying? It's saying, so let's say that there is some observer standing over here in V1, this observer and the source was over here, right? So there is a field that is emitted by this guy. This field is going to get scattered by the object in all possible ways, right? The observer here, supposing there was no object, what would the observer see? There is no object, only the current source and the observer. Only the source field, there is no object. So this is the incident field. No object. Now we introduce a new, now we introduce this object over here. What happens is, I interpret this second term over here as, what should the interpretation be of the second term? Scattered field. We had defined this quantity earlier, that the difference between the fields in the presence and absence of an object is called the scattered field. So this second term over here is called the scattered field. Okay, due to object. Right. So that, and on the left hand side, this thing over here is what is called the total field. So total field is the sum of incident and scattered field. Okay, intuitively that always made sense, but now we are seeing it mathematically. Okay, this, as I mentioned, is also known as the mathematical form of Huygens principle. Okay, now let's see how that is. So what is this saying? The total field is now coming due to something that was originally there, and where do all of these, this second term over here, where is it non-zero? It's purely a surface integral, or in the 2D case a line integral. So these are like secondary sources that are on the surface of the object, right? So in the very beginning, when we started our discussion of this Young's double slit and all, we said that there are these secondary sources at the corners of the slit and they are emitting. So these are exactly like those secondary sources, because what is their location? Their location is only on the boundary of the object, okay, and they are responsible for creating the scattered field. So there may be anything happening inside this object. This object can have any epsilon as a function of r. What we have done is, we have somehow converted that into these equivalent surface currents. Actually, these are surface currents. These are called impressed surface currents. Okay. So this is the mathematical form of Huygens principle. What is the physical interpretation of the second term? This is when r prime belongs to V2. So if I go inside the object, what is the interpretation? The interpretation is that the incident field is exactly cancelled or equal to the scattered field inside the object. That does not mean that the field inside is 0. It just tells you that this balance of these impressed currents, as they are called, is such that outside the object it produces the correct field, inside the object it cancels the incident field. Okay, and this is the second term is, as I mentioned, extinction theorem. Okay, but don't worry about V2, because V2 will have its own equation, right? So far everywhere you see the subscript 1 over here. So this was for V1. When we go to V2, remember what was the variable for the fields inside V2? Phi 2, right? We had said phi 2 is the field inside V2. These equations don't talk about phi 2, they only talk about phi 1. So, and integration over volume 1. So this is telling me correctly what the fields are in V1. Okay, no problem. So now let's sort of take all the, now that we have done all the derivations, so we can just keep the final form.
Phi 1 is the net field through volume V1.
Yes, phi 1 is a net field, that's what we had assumed in the very beginning. Volume 1 phi 1, volume 2 phi 2. Okay, so now let's put all of these volume 1 and volume 2 together and see what happens. Okay, so that's formally the Huygens principle and extinction theorem. This is for phi 1. Okay, so this is for phi 1 over here. the same equation that I had written before, phi incident, and this second term over here is the scattered field, right. I can repeat the same process for volume 2, right. So, if in case you forgot, this was my V2 and this is my V1, right. In volume 2, was there any current source? No. So, how will this equation be different for phi 2? It will be identical, except that there is no incident field term. That incident field term came as the integral of the current, but there is no current in volume 2. So, when I repeat this derivation, this is exactly the field that I will get. Okay. Another important thing to note, this scattered field term over here had a minus sign because the normal was inward. In the second term over here, what is the sign over here? Plus. Why? Because I am using the same n hat, and for volume V2, this is a outward normal. So, everything is consistent. Now, evaluating that delta function in the case of region 2, again the situation is reversed over here. When r prime belongs to V2, the field is phi 2, and when r prime is outside of V2, that sits in V1, then that delta function is not there in that region of integration. So, its answer is 0. So, what is the physical interpretation now? So, this one we have already interpreted. In this case, what is it saying? That if I am inside V2, the field is simply the field that is produced by these surface currents, right. Phi 2 is equal to this. So, somehow what we have managed to do is we have managed to remove the volumes and talk only in terms of currents on the surface. That is why these that is why the whole module is called surface integral equations. It is the boundary. Yeah, by surface I mean boundary. In 3D a surface is a surface, in 2D the surface will be just a line enclosing it, right. And to make sure that it is a surface or a boundary we are talking about, the best indication is that this integral is the symbol of integration is the contour integration, right. So, boundary integral. Actually, also in the literature, instead of surface integral, you will find that these are called boundary integrals for the same reason. They mean the same thing. Okay, so that's the story so far about these impressed surface currents. They are acting in some very strange way where they cancel the fields in and outside, such that the field here is phi 1 and the field here is phi 2. Okay. Now, even so far we have yet to encounter our boundary conditions. Okay. So, but the good thing is that we have separated the physics into region 1, region 2 and one term on the boundary. So, that boundary term is where we will get to impose the boundary conditions. Right now it does not seem very clear how we will do it, but let us go towards it. Okay. So, let us formulate these integral equations. So, what I will do is, now to solve these sets of equations, I am going to take these bottom equations. Okay. These were the extinction theorems, both of these were extinction theorems, and both the top ones were the Huygens theorems. Okay. So, I am going to take the bottom equation from each of these sets and just rewrite them. Okay.